Hello! This is a very informal video that reviews the concepts that I expect my students to know as they prepare for their second midterm exam. Our course uses the book Linear Algebra and Its Applications by David Ley, and this midterm covers the material from the sections that I've listed here. You may want to review the videos that I have on each of these sections if you find that you need a more in-depth review of any of them. I'm going to go through each section and highlight the concepts and formulas that you need to know, and talk about how to solve problems from each of these sections. We'll begin with section 1.5 on solution sets of linear systems. We looked at homogeneous linear systems, AX is equal to 0, and we looked at non-homogeneous linear systems, A times X is equal to B. With homogeneous linear systems, you can have one solution, and that's X is equal to 0, or you can have infinitely many solutions, and those solutions are X is equal to 0, and then infinitely many others that are not equal to 0. With non-homogeneous linear systems, there are three types of solutions. You can have no solution, one solution, or infinitely many solutions. If A is an n by n matrix, when you have one solution, A inverse will exist, and the determinant of A will not be equal to 0. Let's now go over some example solutions to AX is equal to 0. Since A is an m by n matrix, we say that X is an element of Rn. The first type of solution you can get is when X is equal to 0. That's when you have no free variables and your solution as a point in Rn. The other type of solution you can get is when you have one free variable. And when that happens, your solution is a line in Rn that passes through the origin. The third type of solution you can get is when you might have two free variables. For this type of solution, your solution is a plane in Rn that passes through the origin. These types of solutions are called parametric vector form. For example, if we have one free variable, the parametric vector form would look like this, where you have a parameter out in front, and then it multiplies a vector. Let's now look at example solutions to AX is equal to B. They're just like the ones that we saw up above for AX is equal to 0, but slightly different. The first one, X is equal to a vector P that is not equal to 0. This happens when there are no free variables and our solution is a point in Rn. The second type of solution you can have is when you have one free variable and your solution will be a line in Rn through point P, parallel to the line in the solution to AX is equal to 0. If you have two free variables, your solution is a plane in Rn, again through point P, parallel to the plane in the solution to AX is equal to 0. The other concept that we looked at in this section is when you solve AX is equal to B and you have lots of different B's. To do this efficiently, what you'll do is you'll take A and you'll augment it with all of the B's that you have, put it in reduced echelon form, and then find your solution X. This way you only have to do row reduction once. The next section that we looked at was on balancing chemical equations. I listed 6 steps that you can follow for this. The first one is that you have to identify the chemical elements. The second one is you create a vector with those elements. You then create a homogeneous vector equation. You first write the vector equation just like it comes from the chemical reaction, and then you pull it to the left and write it as a homogeneous vector equation. You then solve the homogeneous equation by putting it in reduced echelon form, and then you get your solution for x1, x2, x3, x4, or however many x's you have. You're then going to put your solution in parametric vector form and choose the value for the free variable, and this is the important part. So all the components of x are positive whole numbers. And then the last step is to just write the balanced chemical equation. Our next section is section 1.8, where we introduce linear transformations. We had a linear transformation T of x that we defined to be A times x is equal to B. We said our A was m by n, and that means our x had to be n by 1, and then our right-hand side B had to be m by 1, so that all the sizes of the matrices and vectors work out. Our x is an element of Rn, and their domain is Rn. Our T of x, or B, is an element of Rm, and our codomain is equal to Rm. We can think of B, our right-hand side, as all linear combinations of the columns of A, and that's also called the range. X is called our preimage. When you need to find the domain and codomain, you can look at the size of A and then figure out what the size of X is and the size of B is, and that will then give you the domain and the codomain. Alternatively, if you're given A, you can look at the size of A, and from there you can find the domain and the codomain. One of the concepts we looked at in this section was how to find the image of a vector x, and to do that, all you do is you multiply x by matrix A. We also looked at problems where we wanted to find x whose image is B. This one takes a little bit more work. For this one, you're going to take A, augment it with B, and put it in reduced echelon form to solve for x. Another problem that you might be asked to solve is determine if B is in the range of T. To solve this problem, you're going to take A, augment it with B, and put it in echelon form, and then check to see if a solution exists. When studying linear transformations, we learned that there are two conditions for a linear transformation that come from the definition. The first one is that T of u plus B is equal to T of u plus T of V, and the second one is that T of a scalar C times u is equal to that scalar C times T of u. You need to make sure and know these conditions. To show that a transformation satisfies these conditions, what you're going to have to do is you're going to let u be u1, u2, if u is in R2, and then v be v1, v2, and then substitute these back into conditions 1 and 2 and make sure that the left side equals the right side. To determine if a specific T is a linear transformation, you can see if you can write T of x as A times x. Finally, we looked at problems where we needed to determine what a linear transformation does to an arbitrary vector. To do that, what you're going to do is you're going to multiply A times your vector x and then describe how your arbitrary vector changes geometrically. The next section that we covered was section 1.9 on the standard matrix of a linear transformation. We started out by looking at standard basis vectors, E1 through En, in R2, you have E1 is 1, 0, and E2 is 0, 1. This is just like I hat and J hat. We then defined what the standard matrix for a linear transformation was, and that standard matrix is A, and it contains the vectors T of E1 and T of E2. T of E1 and T of E2 form the columns of matrix A. We then looked at a couple of problems. One of the ones we looked at is where we were given the transformation of one vector and what that transformation is, and then the transformation of another vector and what that transformation is, and then we wanted to find the transformation of a third vector. So the way you do this is you're going to write the third vector, that's the one that I highlighted in green, you're going to write it as a linear combination of this vector and this vector, the two vectors that you were given. And then once you have that linear combination done, you just take the transformation of the green vector. I did one of these in example 3 on section 1.9 part 1. You also might want to review example 2 from section 1.9 part 1. That was a pretty lengthy example, so I don't want to go through that in detail in this review. We next looked at geometric linear transformations. And I'm not going to go through all of these. I'll just tell you which ones we had looked at that you need to review. We had reflections, we had projections, we had rotations, contractions, and shears. Those were in section 1.9 part 2. I just want to highlight, this is the one formula that might be helpful to memorize. That's a little bit hard to derive on an exam. That it was for counterclockwise rotation. And I just want to remind you to review your sine and cosine values for those angles. The main idea with these geometric linear transformations is that you start with E1 and E2. I've listed those there. And then see how they transform by doing one transformation at a time. The last topic that we looked at in this section was one-to-one and onto transformations. To determine if a transformation is one-to-one or onto, you're going to take your matrix A and you're going to reduce it to echelon form and you're going to check your pivots. If every column of A has a pivot, that means that each B is the image of one X and your transformation is one-to-one. If every row of A has a pivot, that means that each B is the image of more than one X, and your transformation is onto. This now brings us to chapter 2. The first section in this chapter that we looked at was on matrix operations. We went over addition and subtraction, and remember that to add and subtract matrices, they have to be the same size. And then you just add or subtract the corresponding entries. I gave you an example here of where two matrices can't be added together because they're of different size, and for that you say that they're just undefined. We then looked at multiplying a scalar times a matrix. The thing to remember for this is that you have to multiply every entry in the matrix by the scalar. And I showed you over here what that looks like. We then looked at matrix multiplication and spent a bit of time on this because it can be a little bit tricky. Just want to remind you that when you multiply A times B, it's only going to work when the columns of A match up with the number of rows of B. That's because these two numbers have to be the same. When we multiply AB, we get a matrix. For instance, maybe we get a 2 by 2 matrix that has C11, C12, C21, and C22 in it. For an example, C12, that entry you'll get by multiplying the first row of A times the second column of B. So in general, your entry Cij is just the ith row of A times the jth column of B. We then looked at the concept of a transpose. We notate the transpose of A as A to the capital T, and that's just a matrix with just the rows and the columns switched. For instance, the first row of A would become the first column of A transpose. And then likewise, the size changes. If A is M by N, then A transpose is N by M. We also looked at a property that you need to memorize. If you take the transpose of a product, you have to switch the order of the matrices and multiply B transpose times A transpose. The last topic we looked at in this section is how to use matrix multiplication to find the standard matrix of a linear transformation. I did an example where we had 3 transformations, and the goal was to get the standard matrix. That's this matrix right here. So that standard matrix is equal to your A from your last transformation, which we called A3, times the A from the middle transformation, times the A from the first transformation. So the order that you have to multiply these matrices in is in reversed order. Section 2.2 was on the inverse of a matrix. For a 2x2 matrix, we got the formula for the inverse of a matrix. That formula is right here. You need to make sure and know that. And then also notice that the denominator in this formula is the determinant. And the denominator can't be equal to 0 if A inverse exists. So that's why we say that the determinant can't be equal to 0 if A inverse exists. We then looked at a problem where we needed to solve a linear system that looked like this. So it's like a 2x2 linear system. So there was 3 steps we had to follow. We first had to find A, and then we found A inverse, and then we were able to find X by multiplying A inverse times B. We then looked at 3x3 matrices. I just wrote down an example of a 3x3 matrix, and we wanted to find A inverse. So the algorithm that we used to do that was that we had to take A, augment it with the identity. I gave an example of that right here. And then what we did was we put it in reduced echelon form. And when you do that, your A becomes the identity if your A inverse exists, and then your identity becomes A inverse. You can check your answer. I love these linear algebra built-in checks. If you multiply A times A inverse, you get I. So just remember, if you are finding the inverse of a 3x3 matrix like this, and in the course of your row reduction, you end up with a row of zeros, that means that there's going to be no inverse. And then you can just stop the algorithm right there. We then looked at a bunch of inverse properties. I've listed these properties here. And then along with these, I've listed some transpose properties because they're really similar. So I always tell students when you're memorizing these inverse properties, memorize the transpose property that's just like it. We then use these properties to simplify matrix expressions. I wrote down just an example of one of the ones from my videos that we ended up simplifying, and we did this one in class too. So there's kind of 3 steps, or 3, not really steps, but 3 ideas that you need to keep in mind. When you simplify the expressions, you can use the properties above. That's kind of where you want to start. You want to work on each product separately. Like this one has 2 products. Do the first one and then the second one. And then things to keep in mind are that a matrix B times its inverse is equal to the identity. And then if you take a matrix and you multiply it by the identity, you just get the matrix back. That's just like multiplying a variable x times 1, you get x back. We then looked at how to solve matrix equations for a matrix X. Here's an example of one that we looked at. So our goal was to isolate X on one side of the equation. And there's a couple of rules that we had to follow. You can only multiply on the left or right side of each equation, not in the middle. So for example, with this matrix equation, you would start by multiplying on the left by B inverse, and then on the left by B inverse on your right side of the equation. If you multiply on the left side of the equation on the left, then you have to multiply on the left side of the equation on the right. The next section that we looked at was the invertible matrix theorem. I would suggest that you go back to that section and review this theorem. I kind of highlighted some of it here, and I kind of wrote it in connection to solutions to our linear system, AX is equal to B. So all of the statements on the invertible matrix theorem are true when AX is equal to B is going to have one solution, and I wrote down all the other conditions that are true if you have one solution. Likewise, on the left-hand side and the right-hand side, if you have no solution or infinitely many solutions to that system, then all the conditions in the invertible matrix theorem are the false ones. Our invertible matrix theorem was an equivalence theorem, which means all the statements were either true or all the statements were either false. Here's a couple of other topics that we looked at in that section. We defined what upper triangular, lower triangular, and diagonal matrices were. And then we talked about, for these types of matrices, as long as there's not a zero along the diagonal entries, A inverse exists. And that also the determinant, again, as long as there's no zero along the main diagonal, the determinant is just the product of the entries along the main diagonal. So in this example, our determinant is equal to 4, and it wasn't equal to 0, which coincides with the fact that A inverse exists. We then turned our attention to inverse linear transformations, and we found that A inverse times X is equal to what we call our inverse linear transformation. Related to this inverse linear transformation, in our homework assignment, we talked about transition matrices. Okay, so I just kind of summarized these transition matrices. The formula is x sub k plus 1 is equal to A times x sub k. So x sub k plus 1 is our next state. And then x sub k is called our current state. And then A is our transition matrix. We can also see that our next state can be written in terms of the original state by multiplying by the transition matrix A to the k. And that's just the transition matrix for state k. Likewise, if we have the formula x sub k minus 1 is equal to A inverse times x sub k, A inverse is our transition matrix for what we would call 1 day, month, year, whatever time period you're working with before the current state. Section 3.1 was on calculating determinants, and we looked at formulas for calculating 2x2 and 3x3 determinants. The formula for calculating a 2x2 determinant is right here. You just multiply the entries along the main diagonal and then subtract off the entries from the off diagonal. For 3x3 matrices, we found 3 ways to find the determinant. We could find the determinant using cofactor expansion, the rule of Serous, also known as the shortcut method, or row reduction to echelon form. If we do cofactor expansion, you have to determine what row or column to expand along, and you always want to pick the row or column that has the most zeros to minimize the number of determinants that you have to calculate. I just gave a formula here if we were to calculate our determinant by cofactor expansion along the first row. And one thing that is always confusing to students is this sign factor. So I always say one thing that you can always do is you can start in the upper left-hand corner with a plus and then go to the right or go down, alternating with plus or minus. So if we look at A23, that would have a negative with it. And the reason for that is minus 1 to the 2 plus 3, adding the entries in the subscripts, and that's equal to negative 1. In general, our formula for Cij is minus 1 to the I plus j times matrix Aij, and that's just the matrix that remains when you cross out the row and column common to Cij. We then looked at the rule of Sarus. That only works for a 3x3. I told my students, please don't do this for a 4x4. It's not going to work. What you do is you take the first two columns, you write them to the right of your matrix, and you want to write them really neatly because you got to look at the diagonals. You then multiply the entries highlighted in blue, going from the top left to the bottom right. And then you subtract off the entries that I've highlighted in pink, going from the upper right down to the lower left. We then looked at row reduction to echelon form, and we kind of went over 3 steps that you need to follow. The first step is to just take your matrix A and put it in echelon form. And then step 2 kind of goes with step 1. You're going to mark your changes as you go along. For instance, if you have a common factor in a row, you're going to pull out that multiple. For instance, if every row is a multiple of 2, you're going to pull out a factor of 2. And then if you swap rows, you're going to have to make sure and notate it by a negative 1 because swapping rows changes the determinant by a negative 1. And then your last step is to kind of keep track of all those changes and then multiply that number by the entries along the main diagonal. And that's going to give you your value of your determinant. The nice thing about row reduction to echelon form, you end up with a non-zero entry, and then the rest of the entries in that column are zeros, which makes it really easy to calculate a determinant. We then looked at section 3.2 on properties of a determinant. I've listed the properties that we talked about here. Keep in mind, number 3 is the one that's usually missed by students. You have to multiply by k to the n, and that's because each factor k multiplies each row of A, so you're basically pulling out a factor of k that corresponds to each row of A. And then we talked a little bit more about theory. If A is invertible or non-singular, your determinant is not equal to 0. If A is not invertible, which is called singular, meaning there is no A inverse, then your determinant of A is equal to 0. Remember that you can only take the determinant of a matrix that is a square matrix. We then also talked about the determinant of a lower triangular, upper triangular, or diagonal matrix. And this determinant is just the product of the entries along the main diagonal. Okay, this is the last page. We talked then on section 4.1, and that was on vector spaces and subspaces. This was kind of our venture into a little bit more theoretical mathematics. We looked at a vector space V, and our vector space contained a vector U, a vector V, and then all linear combinations of U and V. In order for a set to be a vector space, it has to be closed under addition, and you can show that by making sure that vector U plus vector V is an element of your vector space. And then we said that it also has to be closed under scalar multiplication. And to do that, you can multiply a vector by a scalar and make sure that it is also in your vector space. We then looked at subspaces. we have a vector space V, and then we have a subspace H. I kind of said that wrong. We have a subspace H, and it's just a vector space that is a smaller part of a larger vector space. Keep in mind that a subspace is also a vector space. We then looked at a lot of problems to test if a given set is a subspace of a vector space. We have to check three things. The first thing we check is that it contains the zero vector. We then test for closure under addition by adding u plus v and making sure that it's an element of our vector space V. And then we test for closure under scalar multiplication, making sure that a scalar times our vector u is in V. So all three of these checks or tests can be done graphically, but I just want to caution you, if you do it graphically, which I love, we did this in class and on the videos, you have to accompany your explanation with some words to kind of explain what's going on in your graph. Or you can do it completely algebraically. We also did it that way in class and in the videos. Okay, we're now at the last section that's going to be covered on our midterm. That's section 4.3, and it's on the basis of a vector space. So a set of vectors will be a basis for a vector space V if two conditions hold. The first condition is that the vectors in the set have to be linearly independent, and the second condition is that the vectors in the set have to span V. In class, we talked about what that means and also talked about that in the videos. I now wrote down what we need to do in practice to determine if a set of vectors is a basis for a vector space. There's two different things you can do. The first thing you can do applies if the number of vectors in your set is equal to the number of components in each vector. I gave you an example what this might look like. Here we have two vectors and each vector contains two components. So when this is true, when you put it into a matrix, your matrix is going to be a square matrix. So what you can do is you can put these vectors into a determinant, okay? Because again, it's going to be square. If the determinant is equal to 0, then your vectors do not form a basis. They are not linearly independent and they don't span V. Or if it's not equal to 0, it is going to be a basis, and the vectors are linearly independent and they span V. Alternatively, if the number of vectors in your set is not equal to the number of components in each vector, for example, over here, we have 3 vectors, but only 2 components in each vector. When we put that into a matrix, that matrix is not going to be square, so we can't use the determinant. So instead, what we need to do is we're going to take our vectors, put them in the matrix, and we're going to put it in echelon form because what we need to do is figure out pivots. If every column has a pivot, our vectors are going to be linearly independent. And if every row has a pivot, our vectors are going to span V. Keep in mind that both of these cannot be true at the same time, because if every row has a pivot and every column has a pivot, our matrix is square and not rectangular like we're looking at right here. This calculation will help you to determine why a set of vectors is not a basis, because you can tell maybe the set is not linearly independent, or maybe the set doesn't span V. So this was just a brief review, just to kind of highlight these concepts. Now the hard work begins. You guys need to make sure and go over all of the class notes or videos. You need to rework all of the homework problems, all of the learning assistant sheets, and everything else that we posted on the review sheet on Canvas that you need to go over. Good luck studying. Again, the best way to study is to just work lots of problems and make sure that you can work the problems on your own without looking at any materials. Good luck studying.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.